Hello everyone, welcome to the 5th week of problem solving session for the deep learning course. Can any of you confirm if my screen is visible?
Yes, madam, it's visible.
Okay, thank you. So, let's start with today's session. I am Tanuka from ISC. So, today we'll be talking about some neural network problems like feed forward neural network problems and back propagation algorithm, some problems on this sort of topics. So, let us start with the problems for today. The first problem we have is in a simple MLP model, multi-layer perceptron model, with 10 neurons in the input layer, 100 neurons in the hidden layer and 1 input in the output layer. What will be the size of the weight matrices? So, here you have 3 layers. In input layer you have 10 neurons, 10. You have one hidden layer, there you have 100 neurons, 100, and you have one output layer where you have a single neuron. Now you have to tell what is the size of the weight matrix between the hidden and output layer and input and hidden layer. So, as we know, each of these neurons in each layer, let us say the ones in the input layer, will be connected to the each of the neurons in the hidden layer through some weights. So, all these will be connected and will take a linear combination of all of these at the output of this neuron. Similarly, it will also be connected with all of these. This is how multi-layer perceptron model is designed. So, all of the initial layer neurons will be connected to all of the next layer neuron. Now, how do you compute the output of the first neuron at the hidden layer? So, let us say this is x1 to x10. So, you generally do a linear combination, which is let us say wi xi plus you have some bias term I, here you have 1 to 10. So, each of these neurons, this is x1, this is connected through a weight w1 to the next neuron. Similarly, next one is x2, it is connected through w2, and you do this linear combination w1 x1 plus w2 x2 like that till w10 x10, and you have one extra bias term. Now, after doing this linear combination, you apply some sort of non-linearity on top of it to get the output. So, here these wi's are basically the weights. So, you can write this as w transpose x plus b. So, if you write the w's as if you write the weights as a vector, let's say you write your w's as this w1 to w10, this is your capital W. Then you simply doing w transpose, which is w1 to w10, and capital X is your inputs x1 to x10 plus b. So, you are simply doing the same output as before. Here whatever you are doing, this is the same as this. Now, you have 100 such neurons. So, all of these will do the same operation. So, for all of these there will be this sort of a weight vector. Now, if you concatenate all of these together, you can do the entire operation involved in the first input layer to hidden layer transition through one equation only, which is w transpose x plus b, where your w has all the weights. So, w1 let's now make it w11, this is corresponding to the first neuron, let's say. So, w11 to w110, then you will have w21 to w210, like that you can concatenate all the weight vectors, and you can do the entire computation as a whole in W transpose X plus B. So, if you do that, you can see the dimension of this matrix is going to be 10 cross 100. So, each column is the weights corresponding to one neuron in the hidden layer. So, it will have 10 components connecting all the 10 neurons from the input layer, and similarly you will have 100 neurons. So, 100 columns. So, overall the weight matrix size will be 10 cross 100 for the input layer to hidden layer. Now, from hidden layer to output layer, in the output layer you have just one neuron. So, all of your hidden layer neurons are connected to the output layer neuron. All of your hidden layer neurons are connected to your output layer neuron through some weights. So, here you have just one neuron in the output layer. So, your weight matrix will have certainly only a single column as we explained earlier, and it will have in that column all the weights associated to all the 100 neurons in the hidden layer. So, this weight matrix will be 100 cross 1. So, your input to hidden layer weight matrix is, let me write it here. Input to hidden layer weight matrix size is 10 cross 100 and hidden layer to output is 100 cross 1. So, and option D is the correct answer as already mentioned by Pooja. So, this is how you compute the weight matrix sizes in case of a linear multi-layer perceptron or a feed-forward neural network. Okay. Now, given that, the next problem is, consider again a fully connected neural network with input, one hidden and one output layer with 42 and 1 nodes respectively in each layer. Then what is the total number of learnable parameters without any biases? So, the learnable parameters in a neural network are basically the weights and the biases of that network. So, here we are considering no biases for this particular network. So, only the weights. So, you have to compute what is the total number of weight parameters involved in this network that you can learn. So, can any of you give that answer? How many learnable parameters, or in this case how many weight parameters will be there in this particular network? Pooja is saying 82. Anyone else? Yashas also is saying 82. Yeah, you guys are of course correct. So, I will explain it for the others once. So, in the input layer as given, here you have one input layer, one hidden layer and one output layer. In the input layer you have 40 neurons. So, 40 neurons in the input layer. Then in the hidden layer you have just 2 neurons, and in the output layer you have just one neuron. So, here in this layer all these 40 neurons are connected to all of these 2 neurons. So, for each of these 2 neurons there are 40 weights involved. So, for 2 of them 80 weights are involved. So, for the first layer you have 80 weights, and what will be the dimension of the weight matrix here? 40 cross 2 will be the dimension of the weight matrix, and you have total 80 parameters. And in the second layer you have just 2 hidden layer neurons which are going to a single output layer neuron. So, your weight matrix here is 2 cross 1. So, you have just 2 weight parameters. This is just a single neuron which is combining these 2 neurons from the hidden layer. So, just these 2 weights. So, you have 2 learnable weight parameters here. So, if you consider the entire network, you have total 82 learnable parameters. So, option B is the correct answer. I hope this is clear to everyone. We have one more similar sort of question. So, let us say you would like to train a fully connected neural network with 5 hidden layers, each with 10 hidden units, and the input is 20 dimensional. The input is 20 dimensional, output is a scalar, that is single dimensional. Then what is the total number of trainable parameters in your network? Here also we are not considering any bias. So, here what the situation is, you have one input layer, the input is 20 dimensional, which means in your input layer you have 20 number of neurons. So, these are the input neurons. So, it is same as the dimension of your input vector. So, you have 20 neurons in the input layer. After that you have 5 hidden layers. In all our previous problems we had only a single hidden layer. Now we are going into deeper networks. So, we have 5 hidden layers. Let us say H1, H2, like that you have till H5. And each of these 5 layers has 10 hidden units. So, this has 10, this has 10, similarly this also has 10, and the output layer is a single dimensional because output is scalar. So, you just need one neuron to represent that. So, as we have already done for the previous examples, so in this first layer, how many weight parameters will be there? So, each neuron is connected to 20 neurons from the input layer. So, each neuron has 20 weight parameters, like that you have 10 neurons. So, 20 cross 10 or total 200 weight parameters will be there, and the weight matrix size is again 20 cross 10. Now, from hidden layer 1 to hidden layer 2, you are going from 10 neuron to another 10 neuron. So, each of these hidden layer 2 neuron is connected to 10 neurons from the previous layer. So, each one has 10 associated weights. So, total 10 associated weights each for 10 neurons. So, you have total 10 cross 10, 100 weights involved in this layer. Now, you have the next hidden layers also have same 10 number of neurons. So, for all the hidden layers you will have this same 10 cross 10 number of weight matrices. So, you will have this into 4, right? Yeah. Because one set of 100 weights between hidden layer 1 to hidden layer 2, then next set between hidden layer 2 to 3, then 3 to 4, then 4 to 5. 4 set of such 100 weight parameters will be there involved within the hidden layers. Okay. Now, at the end, from the 5th hidden layer to the output layer, how many weights will be there? So, 10 neurons are there in the 5th hidden layer and a single neuron is there in the output layer. So, all of these 10 will be connected to that single one. So, you have 10 cross 1. So, 10 number of weight values involved in this last layer. So, total, if you see the equations given, so this is the total number if you do that. So, 20 into 10 plus 10 into 10 4 times plus 10 into 1. So, option B is your correct answer for this. So, this initially we just considered single hidden layer. Now, in this problem we have considered multiple hidden layers. So, this is kind of a deep neural network, and this is the how the weights are there inside the network, and this is how the weight matrix dimensions and the number of weight parameters are for this sort of a network. Now, Now the next one is, consider an MLP with D nodes in the input layer, M nodes in the hidden layer and K nodes in the output layer, and all nodes are using sigmoidal activation function. So input layer D nodes, hidden layer M nodes and output layer K nodes. First question is, how many weights and biases does the network have? Can one of you answer this? Weights will be dm in plus mk, absolutely correct. So input layer has d neurons, hidden has m neurons, so in between you will have d cross m number of weights, and between hidden and output layer you will have m cross k number of weights. Now how many biases will be there, can anyone tell? Yeah, so Pooja is saying the number of biases will be m plus k, absolutely correct. So how many biases do you have in a network? So for each neuron, when you are computing the W transpose X plus B, this B is your bias term. So for each hidden layer neuron, you have one bias term. You are just doing a linear combination of the input neurons and you are adding one bias term to it. That is happening for each neuron in the hidden layer. So you have one bias term associated with each neuron in the hidden layer. So you total have m bias terms. Now in the output layer, again you have k weights, which are k neurons, which are again doing the same function. So each of these k neurons are again adding one bias term to the linear combination input to this. So you have total m plus k number of biases. Now the next question is, how much computation is needed for one forward pass? By how much computation, what we want to see is how many multiplication we need to do, how many additions we need to do, and how many activation function evaluations we need to do. So you have input layer with m nodes, hidden layer with input layer has d nodes, d m, output layer has k nodes, right? Now how do you compute the output? As we have said, if I consider one neuron in the hidden layer, you have m neurons, if I just consider one neuron, what is it doing? It is doing summation of wixi plus d, right, where I is from 1 to d in this case, because you have d neurons in the input layer. Now each of the neuron is doing this thing and adding one activation function on top of it. That can be any activation function. Here we have said that it is a sigmoidal activation function that is added. Now each of the neuron is doing this and generating some output. Then again the k neurons in the output are doing the same operation on the outputs of the hidden layer. So here if you see this particular operation of a single neuron, so we consider these three types of operations, then for one single neuron, let's say for one neuron, you have to do this WIXI multiplication for I equal to 1 to D. So here you have D number of multiplications. Now how many additions? So while adding these D number of WIXIs, you will have to do D minus 1 number of additions, and another addition is there for adding this bias term. So here also total you have D number of additions, and you have a single activation function evaluation for one neuron. This is the case for a single neuron, the counts for the different operations. Now if you consider the hidden layer that has m neurons, so each neuron will be performing this operation. So you will total have dm number of multiplication, dm number of additions, and you will have m number of activation function evaluations. And in the output layer you have again k neurons. Here each k neuron is connected to m neurons from the previous layer. So in this case, in each neuron of the output layer, your summation of this wi, let's say here we write it as yi, maybe w dash I for the widths of hidden layer to output layer, yi plus b. Here your I goes from 1 to m because you are combining over the hidden layer outputs, and you give the same activation function on top of it. So here in this case you have for each neuron m number of multiplications. This wi dash yi, this is happening for m numbers. So total you will have mk number of multiplications. This part was for hidden layer, this part is for output layer. Now addition, for one single neuron you have m number of additions. So total you have again mk number of additions, and each neuron has one activation function, so total k. So if you totally compute, multiplication you have dm plus mk numbers, addition also you have dm plus mk numbers, and activation function you have m plus k numbers. So this is the total number of computations in terms of multiplication, addition, and activation function evaluation involved while you do one single forward pass through the neural network, this kind of a feed forward neural network. So this is just your one single feature vector is going through your forward pass feed forward neural network through one single pass. Like that you will have to do for all the input feature vectors, then you have to update the weights and keep on doing this forward passes multiple times. So this is kind of an estimate of the computational complexity involved. Now once you have done the forward pass, you have got some output at the end. Now you have to update your weights and biases in the network based on the error between your predicted output that you got through your forward pass and the target vector that you already know. So that is done using the backpropagation idea. So this problem is based on that. Here this is the neural network that is given to you. Some weights are already given and bias terms are also given here. So you can think of it as this is the random initialization for this particular neural network. So if we read the problem, it says consider the following feed forward network. All weights and biases are shown in the figure. All nodes except the input nodes use sigmoidal activation function. So except these two nodes, all are sigmoidal activation function. suppose the input is given by x1 is 1 and x2 is 0.5. x1 is 1, x2 is 0.5 and the desired output vectors are 0.5, 0.5. So, you want 0.5, 0.5 here. Suppose we are using squared error loss. Then we have to find the weight update using back propagation for the weights shown by a thick arrow in the figure. So, we have to find this weight update. Now, if we write the notation for the forward and backward passes, then so here by small k I denote the layer numbers in the network. So, start from the 0th layer, which is your input layer, and you let us say have total k number of layers. So, it goes from 0 to k minus 1. So, at each layer, kth layer, you compute the output for yj. Yj is the output of the jth neuron at each layer. So, this yj k plus 1, this is the in the k plus 1th layer, the jth neuron output is given by this. Now, this you compute as summation of wij k plus 1 yik. So, you consider the outputs of the previous layer, which is kth layer, all outputs from there yik, multiply it with the weights, and in the kth layer you have, let us say, total mk number of neurons. So, 1 to mk this summation goes, and you have one bias term involved also, which is bj k plus 1, and you apply a sigmoid function on top of this. This you have to compute for all the neurons of each layer to get the values of all the entities. Now, here in our case, this is the neural network. So, this will be this input layer is your 0th layer. So, these outputs are basically y1 0 and y1 y2 0. This is y1 1, y2 1, this is y3 this is y2 1 and this is y2 2. So, in order to compute the weight update in this particular weight, first you have to see your predicted output for the given input. So you have to do one forward pass with your given input. So your given input is 1 and 0.5. You have to do one forward pass with this to get the final outputs. So here your y10 and y20 are basically same as your x1 and x2, because only those are connected through it. So your y10 becomes 1, which is equal to x1, and your y20 becomes equal to x2, which is 0.5. Now you move on to the next layer. Now you want to compute y11, this quantity. So here this one is given by this plus this, these two. So you have y10 is connected through minus 0.5 and y20 is connected through 1. So you have sigma of these two wixi, wiyi things, wij, yj actually. So 1 into minus 0.5 plus 0.5 into 1. So I will write it on the top maybe. So y11 is 1 into minus 0.5, that is your y10 multiplied by this particular weight, plus your y20, which is 0.5 multiplied by the corresponding weight 1, and you have to apply the sigmoid function on top of this. This particular neuron, you see there is no bias involved in this, but the lower one, this has a bias term involved. So if you do this, this becomes sigma of minus 0.5 plus 0.5, it becomes 0. Now how this sigmoidal function is? So sigmoidal of x is basically given by 1 by 1 plus e to the power of minus x. So here it becomes half or 0.5. 0.5. This is your y11. Similarly, you can compute y21. Let's compute y21. So if you want to compute y21, you see y10 is connected through 1, y20 is connected through minus 1, and you have a bias term involved, which is minus 0.5 into 1. This is connected like this. So we can also write all of these as a augmented feature vector and a augmented weight vector. That representation also you can do. Then this minus 0.5 is taken as the weight, augmented weight, and this plus 1 comes as the augmented feature. So here while computing y21, what you get is y21 will be 1, this is 1, so 1 into this weight 1, so 1 plus y20 is 0.5, that is connected through minus 1, this path. So you have minus 0.5 plus from the bias term you are getting again minus 0.5. So again you have sigma of 0, which is 0.5. Okay. So both y11 and y21 are 0.5 in this case. Now we have to compute y12 and y22. Let's do it here. So if you want to do y12, that will be basically sigma of like this. So here your y11, so y11 is connected through w111, w112, that is 0.5. So y11 is 0.5, connected through w112 is 0.5. So here you have 0.5 into 0.5. Next your y21 is this. This is connected through this weight, which is w212, that is 2. So 0.5 in 2 into 0.5, plus here there is no bias term involved, so this is 0. So can someone compute this answer? Okay, maybe so if you compute this, it will give as 0.777. Similarly, you will have to compute y22, 0.77. Yeah, yes, correct. Now last one is y22. So how do you compute y22? Here you have again y11 is 0.5 connected through 1, and y21 is also 0.5 connected through 0.5. So 0.5 into 1 plus 0.5 into 0.5. 0.5 into 1 plus 0.5 into 0.5, plus here you have a bias term which is minus 2. And if you do that, you will get 0.223. So these are the two outputs for your network with the initialized weights and the input given. These are the two outputs. Now you have to compute actually the weight update. So for that you have done the forward pass through this, and you have got the final output as this. Now you have to compute the error and back propagate the error from the last layer to the previous layers to see the updation of weight for this particular neuron. So how do you do the back propagation? If you write down the formula for backward pass, that will be something like this. For the last layer, which is the capital Kth layer, there the error is, since this is this formula is with considering squared error loss. Here dj is your desired values at the output layer, so which are the 0.5, 0.5, d1 and d2. For j equals to, here in this case generally this is 1 to mk, here in this case it will be 2, you have 2 neurons. Now this is for the final layer. Now you have to propagate this error to previous layers. For that what you do is, for small k equal to capital K minus 1 to 1, you have to do this formula. You can derive that formula if you consider the squared error loss. this will be your errors back propagated at each of the layers. Now, with this back propagated error, you need to update your weights. So, how will that weight update will be? That's how you generally have it using gradient descent algorithm. So, your weight updates will be this way: wij of the kth layer for the t plus 1th iteration will be wij for kth layer tth iteration minus eta times delta jk into yi k minus 1. So, this is the total back propagation formula or backward pass formula. So, for one input vector you compute the forward pass output. Now, you compute the backward pass errors through these steps, and with this back propagated error you can update your weight vector like this. So, let us compute this for our example. First, we have to compute the error at the very last layer, that is delta 1 2 and delta 2 2, that we have to compute first. Let us first compute delta 1 2, and this is the formula for the last layer. So, this is, if you put that, your here both your j is 1 and k is 2. So, it will be equals to y1 2 1 minus this will be for delta 1 2, which is the error at this neuron. Okay. If you put these values, you can see first you need y1 2. So, your y1 2 is 0.777 to 1 minus 0.777 to 0.777 minus 0.5, because both of your desired outputs are given as 0.5 0.5. You can simply compute the this thing, you will get the output as 0.048. This is the error at the last layer's first neuron. Similarly, you will have to compute the last layer's second neuron. So, that formula will be y22 into 1 minus y22 into y22 minus d2. Okay. That will be the formula for the second neuron. And what is y22? y22 we computed as 0.223. So, if you have this, you compute, you get the final error contribution as minus 0.048. So, these are the errors at your output layer. Now, you have to back propagate this error and you have to compute the errors at the previous layers. So, you computed the errors at the final layer. Now, you compute for the previous layers. So, this weight that you need to find the update is, let us see which weight is this. This is basically W111, right. This is how you So, this is basically connecting the first neuron of the first layer to the first neuron of the next layer. So, that one is W111. So, you have to compute that one. So, if you see this particular formula, here you have to compute W111 at t plus 1. So, that will be Lavanya, your screen got presented. Can you just pause the screen presentation? So here we want to compute W111 update. So that will be equal to W110, no sorry, W111 only at tth iteration minus eta times delta 11 to y10, right. So you need to compute delta 11. That's why I did the simplification of this equation to see which delta you need to compute to get the weight update for the particular weight we want to compute. So you want delta 11. So currently you have computed delta 12 and delta 22. From that you need to now compute the next layer errors, which is delta 11, and you will use this particular formula to do that. So how you do that? This will be y11 into 1 minus y11, within that you have delta 12 into w112 plus delta 22 into w122. This is the formula if you put the values in this particular thing. If you compute these values by putting all the weights, delta values and y values, what you get is, first y11 is 0.5 here. So 0.5 into 1 minus 0.5 is again 0.5. Then delta 12 is 0.048 into W112. So your W112 is basically this one. So the weight connecting the first neuron of the second layer to the first neuron of the next layer, which is this one, and that is also 0.5. So this into 0.5 plus delta 22 is minus minus 0.048 into W122. So W122 means second layer first neuron is connected to the 1 2. So second layer first neuron, which is this, is connected to the next layer second neuron, right, second neuron. So this one, so that weight is 1. Yeah, so if you compute this, you will get as minus 0.006. This is your back propagated error at the required node. So you can simply put this in this particular equation to get the weight updation rule, weight updation equation for the particular weight we want. So that will be eta, you can take any values. Let's say we take eta equal to 1 for now. So it will be just delta 11 into y10. Your delta 11 is minus 0.006 and your y10 is 1. So the final formula becomes W111T plus 0.006. Now what was your W111 initially? It was minus 0.5. So if you do this update, this was minus 0.5. So I'll write it here. So your new weight W111T plus 1 will be minus 0.5 plus 0.006. So this is how you do back propagation through your neural network to update each of your weights. We just computed for one weight. If you want to update all the weights which we do while training the network, you will have to compute all the back propagated errors. So, all the deltas you will have to compute, and using all those deltas you can update all the weights involved in your neural network. If anyone has any doubt in this, you can just post it. I'll take 1 minute break here. If anyone has any question, you can post it. Okay, let us move on to the next question then. The next problem is, you want to build a 10 class neural network classifier given a cat image. So, your input is a cat image and you have, let us say, 10 different types of cat images you want to classify into one of those 10 classes. You want to classify which of the 10 cat breeds is belong to. Now, which among the 4 options would be the appropriate loss function to use for this case? Yash is saying option A, cross entropy loss. Anyone else? Yash is absolutely correct. Cross entropy loss is the loss that we use when we are training our network for classification tasks. That is for classification, whereas MSE or other losses you consider, that is more for regression losses. So, cross entropy loss is the correct one for doing this type of classification. Be it any number of classes, cross entropy loss is the choice for that. Now, let us do the last problem for today's session. So, you have been given a neural structure. So, the question is, which function do the following perceptron realize? Your x1 and x2 can take only binary values, that is 0 and 1, and hx is the activation function, which is given as hx is 1 if x is greater than 0, else it is 0. You have to say what is which gate basically this particular perceptron structure represents. So, if we want to write it, your final output, if we write that as y, that is equal to h of your linear combination, which is your x1 is connected through minus 1. So, minus x1, x2 is also connected through minus 1. So, minus x2, plus you have the bias term which is connected through, which is 1 basically. So, plus 1. This is the output function that is being realized. So, if you want to make the truth table for this, let us say, you can have 0 0, 0 1, 1 0, 1 1. Let us say both your x1, x2 are 0, then in that case your y becomes h of 1. Now, h of 1, so if given this equation, this will be equal to 1. So, 0 0 goes to 1. Now, let us say you have 0 1. In that case, your h is this is 0, this is 1, so minus 1 plus 1, so h of 0, that is your output will be 0. Same thing will happen for 1 0 also. Now if you have minus 1, if you have 1 1, in that case your output is h of minus 1 plus 1, so h of minus 1, which is again you have 0. So for 0 0 only you have 1, all other cases you have 0, which is basically the NOR operation. So this particular perceptron represents a NOR gate. So this is how you can implement different gates also using single neural net, single perceptrons. So these were the problems planned for today. I'll stop solving here. If you have any doubts, you can post it now. The last week recorded session, when will, I guess it's already there in the website. Can you check in the sheet that is there for problem solving session? So we have already given the links, so mostly it will be up.
Ma'am, I can't able to hear, ma'am.
Can you hear now? Am I audible, guys? Okay. Penelope, can you hear me?
Yeah, ma'am. Actually, where it is available, ma'am, I'm unable to get it.
So in the left side pane there is one option for problem solving sessions. Did you see that one? That will have a Google Sheet in it. You will have the links of all the recorded videos as well as these slides.
Problem solving. Yeah.
So both all the 3 TAs that we takes the sessions for this course, all of those links will be in that sheet.
Okay. Yeah. Thanks, ma'am. Okay.
Yeah. Pooja is saying I am not able to solve question 9 of assignment 5. So is assignment 5 solution out yet? In case the solution is not out yet, that I can't tell you the answer for now. Can you just confirm if the solution is given already?
No, ma'am.
Okay. If the answers are not given, maybe we can wait for one more week and next week I can solve it once the answers are out, because I am not supposed to solve this year's assignments before the assignments are done.
Ma'am, Today is my first day. Please send the assignment questions, ma'am.
So assignments are hosted in the NPTEL website itself. You have to go there and solve it within the deadlines. So we do not provide
Okay.
it ourselves.
Okay, ma'am.
Ma'am, answers of assignment 5 are already uploaded. Solution is not uploaded.
Is it? Is it? Then can you? Then we can discuss about it. So can you tell me the question what it is, or can you post it here for now?
Yes, ma'am, sure.
Ma'am, the assignments is how to submit, ma'am.
The assignments you can once you log in into your student account in NPTEL, you can attempt the assignments once you enroll in the course.
Okay, ma'am.
So Pooja, are you talking about this question that suppose the input layer of a fully connected neural network has
Yes,
4
ma'am.
nodes? Okay, okay,
Yes,
let
ma'am.
me just take the question. So it's saying that suppose the input layer of a fully connected neural network has 4 nodes. Okay, so the input layer has 4 nodes. The value of a node in the first hidden layer before applying sigmoid nonlinearity is V. Value of a node in the first hidden layer before applying non-sigmoid V. Now each of the input layers nodes are scaled up by 8 times. What will be the value of that neuron with the okay? So your input layer has, let's say, 4 neurons. Now in your hidden layer we are just talking about one neuron. So what will this neuron do? It basically does this summation wixi. We don't have any bias term for now, let's say. So you have wixi and you have 4 input nodes. So your I goes from 1 to 4 and you have a sigmoidal nonlinearity on top of it. So your V is basically the out value of the node before applying the sigmoid. So this part is your V. Now each of the input layers nodes are scaled up by 8. So initially let's say it was like this, now it has become, all of these are this. So now your next V, your weights are the same only, just your input has scaled. So instead of xi, now you have 8xi and I is same 1 to 4. What will be the value of that neuron with the updated input layer? Yeah, If you can, if you, this is your updated v, I should not write it as v, that's why the confusion is. Let's say write it as v1 is your new value of v. So that is basically, if you take the 8 common, this is your initial v, so it becomes 8v. So can you say what is the doubt? Oh, acha, you got it. Okay. So this the solution is clear, right? How it's coming?
Yes, ma'am.
Okay. Any other doubts from anyone?
Ma'am, these calculations are a little bit tough, and whether calculators are allowed and for the exams.
Sorry, I didn't get your question.
For exams, no, calculators are allowed.
That I'm not sure actually. You have to check with NPTEL support emails. I'm not sure if a calculator is allowed.
Okay, thanks. Ma'am.
And shall we solve assignment questions only after solutions is released? Not you. I will solve only after solutions are released, because assignments are supposed to assess your understanding. So I'll not solve this year's assignment questions before you have done, submitted and got the answers. Yeah, so I unless your submission deadline and your assignment solutions are there, I will not solve for this year's problem. I'll solve similar things only from other places, but I'll not solve the exact ones in your solution unless it's done, your assignment is done.
Ma'am, assignment 5, question number 10. So here in option B, they have mentioned that ReLU function helps in creating sparse representation. So what is exact meaning of this?
So, okay, let me see the question once. Which of the following are potential benefits of using ReLU activation over sigmoid activation? It is sparse representation. So sparse representation, in the sense, if you see the ReLU function is basically, you have for the negative portion your function value is 0, for the positive portion you have the unit slope line. So whenever your neurons output is in the negative portion, you are basically getting 0 output. So sparse basically refers to that you have a lot of zeros in your representation. So if you have a lot of zeros, you can further compress those representations. So those are sparse representations when you have more number of zeros, and that is coming because your entire left side is 0 for this thing, ReLU. That is so these neurons you can think of as their outputs are 0, so those are not at all activated, so the representation becomes sparse. That's the idea.
Ma'am, how to see the assignment questions, ma'am?
Who was this assignment question you are asking?
Lavanya, ma'am.
It's there in the course page itself. Under each week you have the assignment for that week. So where you have all the lectures and all, below that you will have the quiz for each week, and there will be a deadline for each of the quizzes.
Okay. Ma'am, after this course completion, the certificate is provided, ma'am.
Actually, I'm not sure about this administrative part. You will have to talk to NPTEL guys for this.
Okay, ma'am.
Any other doubts from anyone? Madam, how do we ask doubts? You can simply unmute and ask. No issues. So if you have any doubt in any of today's solutions, you can also tell it now.
Hello, ma'am.
Yes.
Money
Yeah.
here. Madam, my question was whether if you share your mail ID, will post the query, whatever it is there.
You can post in the discussion forum itself for the course.
Only we will post it, madam.
Yeah, there you can post. We generally have a look at those, so we'll answer it there.
Okay, ma'am. Madam, what I asked was, if once the solutions we get, no, madam, whatever solutions we get for every assignment,
Yeah.
uh, their steps will not be there, madam. Only the final answer will be given.
No, you get a detailed solution also, right, for the answers.
No, madam. We don't get the
You can
detailed steps.
just check once. Yeah, so for week 5 it is still not there, but till week 4 you can see one option called assignment 4 solution, assignment 3 solution. Those has mostly a detailed version of the solution. Else, if you want to discuss about any particular problem, that you can also tell me in this particular problem solving sessions. We can look into those. Is problem solving questions are different from assignment questions? Yeah, problem solving questions are similar, but not the exact assignment questions you have, but it will help you in solving your assignments.
Ma'am, actually, my question is normally, week six assignments, what are all the questions it's coming, no? Similar questions, no, we can discuss it here so that it will be useful for those next week assignments, no? That will be only useful. Otherwise, no, before submissions, it will not be useful, no?
Yeah, if you have any particular question that you want to discuss, you can just tell me. I'll discuss on that.
Because it's 1 week delay is happening, no, in between.
Yeah, yeah.
Because of that, we are submitting it, and after that only we are getting some idea to solve those questions.
Yeah,
So
so
we are facing some difficulties because most of the things are derivations and difficult to follow. But for me, I am just facing like that. I don't know about others.
yeah, okay. Actually, this time the first class was scheduled 1 week after the lecture started. That's
Okay.
why everything was a bit delayed.
Mama, one more thing I just want to ask. Actually, Tuesday one discussion session is there,
Uh-huh.
but two timings are coming in between. Whether it is, and I am unable to even the second timing unable to log in into. I am facing the problem, but the first timing I could able to, but it is showing some other assignments like auto encoder and last week's session. Whether it is relevant to our course or in some other course, it's connected.
No, no.
Connect.
Those two sessions are also for this particular course only. But I guess the first session that you have, that person, that TA is mainly focusing on coding
Problem.
parts, I guess.
Coding parts. Okay.
Yeah, he is doing the coding part.
But the timing mismatch is coming now, ma'am, because here it's 6 to 8 and other one is
7
7
to
to
9.
9. So
Yeah.
which one we have to log in? That there is a confusion in that.
That is yeah, your choice which one you want to go for. Mostly the 6 to 8 one is coding based, and the 7 to 9 one is problem solving based, and today I have one for problem solving based, so whichever you want to choose.
Okay. Is the is timing, if they keep it in some other different timings, we can attend two sessions also, no, ma'am?
Yeah, that actually I don't know. These timings were, some choices were taken, and based on the best possible availability of everyone, it was allotted like this.
Okay.
So yeah,
Okay. Thanks. That also the record sessions will be there, no,
yeah,
ma'am?
yeah. Recorded sessions will be
Okay.
there.
Thanks.
In the same sheet, you will find the links for all the three TA courses.
Okay. Okay. Thank you, ma'am. Thanks.
Okay. So any other question, guys? Otherwise, we can close today's session if there is no more doubts. I'll wait for 2 more minutes. If you have any more doubts, we can discuss.
Ma'am,
Otherwise,
previous section videos can send, ma'am.
previous what?
Section previous video, ma'am.
Yeah,
Can send, ma'am.
it's
Send me.
there on the course web page. You go to that problem solving session tab. You have a Google sheet there. You have the links for all the recorded sessions, and these PDF links also for these PPTs that we use. So you'll get all the links there.
Yes, ma'am. Thank you.
Okay, I don't see any more queries. Then thank you everyone for joining. We'll again meet on the next Saturday with the next set of problems. Let's close today's session here. Bye guys.